这礼拜六跟日我们有举办在那个我们的中正堂有举办这个排球赛，欢迎大家去参观，150块可以看3场，哎，所以欢迎大家去参观就是这个排球赛，就是六跟日我们用那个技术就是那个运动科技去呈现这个弹幕。那还好，就是没地方去就去走，去坐在那边看看，有表演，有流行舞蹈表演，有一些表演那是台湾的职业队啦职业队来他们比赛了，然后开幕赛在我们这边开幕，所以欢迎大家去参观。那我们会在那边展示我们的科技，有30支摄影机在那边。继续。So we'll continue our lecture about deep learning. Last time we talked about this unit. And this unit, the weight is a W. The input is X. The bias is theta. And after this one, we have the output here. We have an activation function. It's a nonlinear function to transfer this linear combination to the other nonlinear space. We call F, and the output is Y. And usually the output is between 0 and 1 or minus to 1. And the W is here. So the same as we just talked about AX equal to B problems. A is this parameters with homogeneous matrix. X is the input. The Y is the output. The usually the simple way, Y is just a label. Okay, label 1 is only one out of 0, something like that. Okay, so based on that equation, the other format is the same one. So Z in this paper, Z is the input, W is the parameters, F is the activation function, and Y is the output between 0 and 1. So this 1. And then the equation is like this way. So the F is the output, Y is estimation result. This estimation result. D is ground truth. Okay, and we try to decide decision function whether it's a 1 or 0, is a phase or non-phase. Okay, so we do this equation. And we formulate this equation by sum of square difference. However, because we have a batch size, so we are divided by number of batch, so become mean of square difference. Original, this one is the sum of square difference. That's for machine learning. However, in deep learning, because they use gradient descent, they need a lot of iteration. So they divided by the data by mini batch. So the batch size is n. So the result was divided by the batch size n. So this is called mean square error. Okay. And this one is not good enough. So we will include one more term we call regularization term. That's like Lagrange regularization term 去调整，去限制它。Regularization term is try to do some constraint, okay, of this equation, this curve. This curve we try to do some constraint on some small region, so the result will be better. So let's recall regularization term, this term, okay. And how can we? So the equation mean square error is okay, but if you have a regularization term like a Lagrange, the result will be better. Okay. And how can we solve this one? They use gradient descent like this one. So they include the gradient descent here. They include the mini batch size to solve these problems. And how about what's a mini batch? Because the purpose why we want to use mini batch is because in the deep learning, they have many parameters, millions, 10 millions, 100 millions parameters, a lot. But gradient descent, okay, you need to do iteration like this one. We just talk about iteration. We do iteration to approximate the global minima. 就 gradient descent 它是一种要很多次 iteration 去逼近它，所以它需要多一点的 iteration 结果才会好。所以我们为了这个原因 so we do the mini batch. So for example, suppose we have a 60K training samples, okay, and we suppose our batch size is 100 samples. That means 100 samples become one batch. So we have one batch here, second batch here. So each process for one batch we call one iteration. One batch, mini batch, we do process we call one iteration. So in this case, there are 600 iterations. And this, if you complete process all the data one time, we call one epoch. One epoch. 你把这些资料这样整个处理完以后，才称为一个 epoch。但是一个 epoch 有很多次的 iteration， 这是你自己决定的这样子。好，那this is a gradient descent like this one. So we do iteration. And then this one epsilon is the learning rate. Learning rate 就是你每次步伐要逼近的那个速度啦。Learning rate 就是你逼近的速度。那你的逼近速度 ，if a learning rate is too big， 它会跳来跳去。If learning rate is too small， 它花很多时间在逼，你可能逼一个礼拜还没有逼完，还在那边慢逼近这样子所以这个 learning rate 很重要。OK。那 we talk about convolution. So when we do the convolution for deep learning, there are three situations. Because of these three situations, so we do the convolution. One we call local receptive fields. Receptive fields meaning 你的视野，你的 view, the window you can see, they call receptive field. The second shared weight. The third is the subsampling. So for why we want to use convolution? Because we want to extract the features. Okay. So, but not only the extract feature, in the convolution we also think about three things. One is this one. So, for example, there's a window. The window is filter. This is a filter. Filter is the coefficients we want to extract. Okay. So local receptive field is meaning the size of filter. Usually 3 by 3. Sometimes 5 by 5, but usually 3 by 3 is good enough. So the local receptive field, because different parameters of filter, so you can extract the different result we call feature or feature maps. So like the A, we will extract like this way, or extract the sum like a corner, or extract the horizontal lines or vertical line. So that's the extraction result. So we call it, we use a local recession and receptive fields. That's actually that is the filters. The second is we call shear weight. What's shear weight? Because if you do the fully connection, each W is one weight. Okay, so if you do fully connected, there are many connections. So there are a lot of parameters. So we do convolution, we can reduce the parameters. For example, is suppose the input is 5 pixels. The filter is only the 2, the coefficient only 2. So you have a connection from the first one. You connect to here. After you do, suppose you filter, the coefficient filter is 1, 0. So your result will be 2. And you shift the next pixel will be 1, and then 3. So this is your feature map, your result. This result actually is look like this one. Result. Okay. And then if you do the fully connection, right, you will allow for parameters. But if you do the shear weight, you can, like this, I write this result here. That's meaning you can use the same coefficients. For example, the coefficient here only 2. So for each connection, you can have the same coefficients. So you will reduce your parameters to be like only 2. 就是shear weight，就是说我这样做 convolution 完，我事实上一个 filter 就是一组系数，那把这个系数当成你的 connection 的 weight， 这样子。那我这里有写是说，事实上你这个理论上这个因为是 learning， 那个 weight 是 learning 的，那你认出来，假设这1、2、3、4、5、6，你有6个系数，但是你的 filter 是2，所以你可以把它变成3，就是这3个加起来除以3。那另外000这加起来除以3，就变成只有2个系数而已，就变成 filter 的 size。所以你本来 fully connection 会有很多个系数，可是你用 convolution 的时候，你的系数就变成你的 filter size。So what I mean is that if you do the fully connected, suppose this is a 10, this will be the other 10. So your connection, you have a 10 by 10. You are going to have a 100 parameters. Okay, but if you use filter convolution, you can only have 2 parameters. That's coefficient of filters. Okay, so this one. So I write this here. So shear weight can reduce a lot of parameters. Okay, but when you do the transformer, still you use shear weight, you still has millions of parameters. Okay, the last one is a subsampling. Why we want to do the subsampling? Because this is, suppose this original image here, you do downsampling. We use the same 3 by 3 recession field or filter. In the high resolution, the 3 by 3 only can see the local feature. In the low resolution, 3 by 3 can see more global receptive field. 就是说你当 sample 你投放3×3的 3×3的那个的大小，你在高解析度看到是很细微的东西。因为当 sampling 完以后，你在3×3你可以看到比较大范围的东西，这样。OK， 所以这个有它的好处啊。Okay, so we go back to we try to take a look at our topology, the structure. So our example for the net 5 is this way. You input an image. You have a 2 convolution layer, 1, 2 convolutional layer for the net 5. And you have 3 MLP layers. This for classification. So total is 5, 2 plus 3. So they have 5 layers. The net 5 have 5 layers because you have 2 convolutional layers plus 3 neural network layers for classification. And for the downsampling, usually we don't call the layer, just downsampling. We don't count it. Okay. And for each convolutional layer, usually include convolution, batch normalization, and the activation function. So those 3 functions together we call one layer, include convolution, batch normalization, and activation function. Some paper switch activation function and the batch normalization. They switch. But most of cases, they do normalization first and do activation function. And so after this one, this 2D. This 2D. But in neural network, here is 1D. So from 2D to 1D, we need to do the flatten. So but for the 2D, you just flat to be 1D case, 1D vector, and in order to input to the neural network. Okay. And the net 5 is this way. This is the net 5. So input 1, this is wrong. This should be 0, 1, 2, 3 until 9. So our input is from 0, either 0 or 1, 2 until 10. Until 9. The output has a 9 output. Only one output is close to the 1. Other are close to the 0. So if you input 1, you suppose 1, 2, 3, 4, 5 until 9 and 0. 1, 2 until 9 and 0, 10 digits. So the output, if you input 1, the output in the number 1 class will become 1, other are 0. If you input is a 0, your output in the number 10 digits will become 1 and other are 0. That's called labeling. We call labeling. Okay, so this topology of structure is the same as this one. So today we'll teach you what is this one. It's very basic one. So first of all, how many layers? I say that this one layer, this downsampling we don't count. And there's a second layer, and the downsampling we don't count. So there are 2 downsampling we don't count. So 1 layer, 2 layers. So 2 layers for convolution, and 3 layers for classification. So they call the net 2 plus 3, so equal to 5. We call the net 5. But as I said, for each convolution, they will include the input, the weight, the bias, and the summation together. After you do summation together, and then do the activation function, and then output. The output result because of the activation function, so the output will be between 0 and 1. Okay. So first of all, what's the input? In the net 5, the input is gray value image. So the channel only equal to 1. The channel only equal to 1. But right now, we use the RGB camera So RGB is 3 channel. So the input is 3 channel. Okay. So how about filter? Usually we call, even though it's RGB, we call filter is suppose it's 3 by 3. So 3 by 3 because there's 3 channels. So times 3 channels. So what's the number of the parameters for each filter is 27. It's 3 by 3 by 3 channel. So the total parameters is 27. But when people talk about the filter, sometimes they don't talk about the number of channel. They just say, okay, my filter size is 3 by 3. So the parameters is 9. No, it's wrong. The parameter is 3 by 3 and by the number of channels. Okay, so it should be 9. Okay, so be careful about that one. So that's input. So after we have the 3 channel input, but in this case, only 1 channel input after this one. Okay, so what is, I do this way. And then they start to do the convolution. So this is suppose in this case is the image is 5 by 5, and the filter is 3 by 3. 这个例子举例一下是假设 input image is 5 by 5，那 filter is 3 by 3, and they do the convolution. What's the convolution? They do the inner product and shift inner product, So this called scan 9, SCAN, scan, LINE, scan 9. So they from the top left do one convolution, shift, and then one convolution, shift this way. And each time they do convolution, they have one new result. So in this case, suppose their gray value is 1, and 0, either way. But in reality, the gray value is between 0 and 255. Okay, and the coefficients for filter is this one, 101, 101. So it's 101, the red one. The coefficients of 3 by 3 filter and 0, 1, 0 and 101. So this is the coefficients of filter 3 by 3, and the image gray value is the black one, 1, 1, 1, 0, 1, 1. That is right. So after they do convolution, that's meaning the inner product of corresponding point, so it become 4. So the result will be 4. And then shift, the new result will be 3. So finally, this will be the result we call feature map. The original image, after we do convolution, the result we call feature map. Feature map is also one image. Like in this case, original, if I input 3, after I have a first filter, this one result, and this result is feature map 1. And then I have the other filter, have different coefficients. I have a second result. So if I have 6 filters, I will generate 6 feature maps. Okay, so one filter will generate 1 feature map. The second filter will generate second feature map. So the number of filters is decided by you. Okay, and more filter will cause more parameters, but the good thing is that they have a more feature result. This one. Okay, so in our case here, we have 6 feature maps in the first convolution. Okay, so that's meaning we have 6 filters. The first one, okay. And in this case, the filter size is 5 by 5. 5 by 5. But usually right now we use 3 by 3. So this one, suppose the image is 3 by 3 and filter is 2 by 2 and include bias, and our output will be this feature map. I say again, this the other example. If our input image is 3 by 3, our filter is 2 by 2, include, because this parameters and this is our bias, so our result will become 0 here. I calculate here. When we do the coding, this will be like this way. See, this is 2D. This 2D. Okay. But in the neural network, usually it's flattened 1D. So let's see 2, 4, 5, 2, 4, 5. And second row is 1 or 2. So 1 or 2 will be like this way. And they create the map is 1, 2, 3, 4 maps here. Oh, sorry, this is one map. This one map. Right, this one map. Only one map. Okay, so the bias. So the connection will look like this way. So this is what we image in our brain, but in reality, they do is like this way. Okay. And after we create the 6 feature map, and then we want to do the downsampling. The downsampling is this one. So suppose we have a feed the image is this one. Okay. After we convolution, suppose this is only one feature map, and we do downsampling by this one. So downsampling, because how can they do? Downsampling usually 2 methods. One is we call maximal pooling, it's meaning 2 by 2, 4 pixels. We pick up the maxima one to here. So this maximum is -1, put here. This region 2 by 2. Okay, the maxima is 1, so we put here. Because we want to do the downsampling, so the shift is 2 pixels. Because we want to do the downsampling from this one, this is a 6 by 6. Okay. After we do convolution, see, if we do convolution like this one, this way, this is a 5 by 5. Our filter is a 3 by 3. After we do convolution, the image size becomes 3 by 3. Why? Because we lose the information of boundary. I say again, original is 5 by 5. After we use filter 3 by 3, and the result becomes 3 by 3, because we lose the boundary. Because when we start, I do this one. See, because the first filter here, okay, and then result will be the center. So after this calculation, the result 4 will assign to based on centers of here. So we lose the information of the boundary of original image. So the boundary we lose the information, it depends on the radius of the filter. 就是我们的 boundary 损失是那个我们的 filter 的半径。So the radius here is 3 by 3. So the radius is only 1 pixel. So if we use 3 by 3 filter, we will lose 1 pixel of boundary. If we use 5 by 5, we will lose 2 pixels on the boundary. Okay. So that's we lose information. So after here, so after this page 28, after we do the convolution in this example, original image size is 32 by 32. Okay. After we use 5 by 5 pixel filter, we will lose, because 5 by 5, the radius is 2 pixels. So we will lose 2 pixels on the boundary. So left side we lose 2 pixels, right side we lose 2 pixels. So totally we lose 4 pixels. So our image size will be from 32 become 28. 我们会损失2个 pixel boundary， 所以变成28乘28。那我们有 we have a six filters, so we have a 6 feature maps, and then we use 2x2 pooling to do the downsampling, stride by 2, 就每次 shift 2 pixels. So our feature map size become 14 by 14 from 28 by 28. 这样子，所以这里就变成损失掉了，这样子，可以哈。好，那我们再继续看后面。那 for the downsampling, you can use average pooling. You can also use average pooling, but people prove the maximum pooling is better than average pooling because we want to keep the high frequency value, high texture. So that's we choose the maximum pooling instead of average, because good feature is a high frequency. So we want to keep the maximum value of feature instead of average. OK， 那这个就结束了。好，那 how can improve if we don't want to lose the information, the boundary? We call padding, P-A-D-D-I-N-G, padding. So if you don't want to lose the boundary information, okay, you need to do the padding first. 就边缘要把它补零这样子啊。那 padding size is the same as the radius of filter size. So if your filter size is 3 by 3, your radius is 1 pixel. So your padding will be 1 pixel boundary. If you are 5 by 5, okay, your radius is 2 pixels. So your padding will be 2 pixels. That's padding. Okay. 那这个教完了。好。So we finish the first convolution. So right now we have 6 feature maps. And how about the second convolution? The second convolution. In the net, they use different crossover filters. For example, they design 16 filters. There are 16 filters. Right now we have 6 filters. And then that based on the 16 filters, they create the other 16 feature maps. Originally, you only have one image. You have 6 filters. You create 6 feature map. Right now, you have 6 feature maps. He wants to generate 16 feature map. So they need 16 filters. 你要几个 feature map 就要用几个 filter 来产生了，这你 depend on 你自己这样子。好，那这个 filter 怎么做？你看，它这个一开始是 only 3 only cross. You have 6 feature maps. So first filter only consider feature map 0, 1, 2. The second shift 1, 2, 3. So you have 3 in the first 6 filters. You have only cross over 3, and then cross over 4, and then cross over the other 4, and finally cross over 6 feature map. But right now we don't do this way. Right now our crossover is over 6. How many feature map you have? Your filter will cross over entire feature maps. 就之前因为电脑的 记忆体关系，他们之前每次在做这种 crossover 的时候 filter， 它是考虑3个一组，4个一组，4个一组，6个一组。那现在电脑的记忆体够大，所以你在做的时候就6个全部考虑进来，所以你的 filter size 是5乘5乘6个哦，是一次是6个 dimension 哦。好，那我们来看这里。So in the old one, they only consider partial of the feature map become 1。那总共有16个。像这个来，那 right now we don't use that one. We have a 6 feature map. Our filter will include cross all of the feature maps. So we have a 6 channel. And so our filter size will 5 by 5 times 6 channels and become 1 feature map. 这样子。那 we totally we have, so the other one, so this one set of a filter, actually one filter, this one filter is a 5 by 5 by 6 channel become 1 feature map. So totally we have a 16 filters become 16 feature maps. That's it. 这样子。And dimension, because we do not do the padding, so the feature map size will reduce from 14 to 10. So this final result. So this result is this one here. So this second convolution. And then we do downsampling again. So become this 10 by 10 become 5 by 5. So that's it. That we finish the convolution in this case. Okay. So after we finish the convolution here, oh sorry. Right. So after we finish convolution here, and then we do the classification. Okay. We start to do the classification. So we continue. Okay. But in the original ReLU, because from here to the neural network, we do fully connection. That's not good. Why? Because we fix this one to 120. That's meaning if your input image size is different, there will be cause the error. 我讲一遍，这里就这个是旧的ReLU，但是你可以用新的方法来解它的东西，结果会更好。This original, the old, very old ReLU, ReNet, but you can use the new method of deep learning to improve this result, to become better, much better. How can we improve? How can we improve? The first one is we do this one. We do crossover entire feature map. This one we can improve. Original, what they did is that they just pick up 3, pick up 4, pick up 6. But the new method, we can do this. Each time is 6 channels. We consider 6 channels. That's one we can improve. The second one we can improve is this one. We don't do the fully connection. We do the fully convolution. The exam will do this one. 我考试会考这个哦。好，怎么改善这个人类的东西 ？So the original old one is fully connection. That's meaning you connect. So this 120. But what's the weakness for fully connection is because when the input image size is different, it doesn't work. 你若输入影像的 size 不对的话，这里因为你输入影像的 size， if you input, for example, if this is 32 by 32, and then the final one is 5 by 5, the image size is 5 by 5. If I change this one to be 64 by 64, this one will be probably will be 10 by 10, and this cannot work because this one is already fully connected. 它已经全部连在一起了。因为什么？因为它这里的如果 flatten 的话是16乘5乘5哦。这里我要连接120 ，if I do flatten, the flatten size is 16 by 5 by 5. It cannot change. That's the weakness for fully connected. 全连接有这个缺点。那我怎么改 ？How can I improve it? I will change fully connected to be fully connectional. Use filter. 那就可以解决了。你可以解决这个问题。好，你全连接就连着就死掉了。If you do the fully connection, you connect and fix, you cannot change the size of input image. If you want to input any size of image here, you need to change from fully connected become fully convolutional network. And first, RCNN talk about this issue. So you will change this one to be fully convolution, use filter. And then you can solve these problems. Okay. So finally, this what kind of activation function you want to use. Okay. And in the net, they use sigmoid. Each activation function, they use sigmoid. However, when the depth is deep enough, don't use this one. You try to use the redo, because this one is nonlinear computation. It's complicated. It's not good for stochastic gradient descent. It's not good for stochastic gradient descent because each time this value is very deep. 就是它这个曲线太 deep 了。那 deep is meaning the slope is too deep, and the value either 1 or 0. So many values are 0. So it will become vanish. So it will cause if the deep learning is too deep, each time you use sigmoid, you will first of all you will waste your computational time. The second, you will cause easy vanish. This value, your parameter will become 0. That's not good. So if you use the deep learning is deep enough, you should use redo. It's close to the linear process, linear distribution. Okay, 是比较线性的这样子啊。Okay, and other you don't care. I never use others. So just for your reference, I never use those. It's okay. So finally is a output. The output we will use Somax. What Somax is this equation? It's meaning when here the output until the last layer is 3, 1, minus 3. And then you use exponential term. And after you do the exponential term, you normalize the exponential term that the total output value, the summation of the output value become 1. That's Somax. Why we want to use exponential term is because you want your result is either close to 1 or 0. Okay. In the middle of convolution, you don't want your result between 0 and is close to 1 or 0. That's not good. In the middle of the process, you hope your result is close to the original data. But when the output, the final output, you hope your result is either 1 or 0 for the classification. So we use exponential term to let the value not locate at the boundary. The 0.5, that's not good. We want the value. See, the bigger is more bigger, the smaller more smaller. And then we do normalization. So that's called Somax. So that's the final output. Okay. So that's I still have a time. Okay. So the Somax is the final output is this one. After you do this one, you will Somax here to make sure your output is close to the 1 or 0, not located at a 0.5, because 0.5 is the uncertainty. It's not good. Okay. And I think time is up. I will stop here. Okay. And finally, I talk about this, the loss function. There are 2 loss functions. One we call mean square error. I talk about the other cross entropy. What I try to say is which situation use a mean square error if it's continuous. If your output is like a bounding box, it's continuous approximation, you use mean square error. If your output is a classification, you use discrete data, use cross entropy. That's important. Sometimes students mix up this one. It's not good. 记得这个是 continue for mean square error and cross entropy for discrete data 就 classification。OK， 那这个是让你参考，大概我讲完的。OK， so that's all for this lecture. OK, so next week we'll go next lecture about deep learning. OK, so that's for today. Thank you.